Now, if I randomly generate two linear equations by randomly generating a number in front of x, a number in front of y, and a number on the other side of the equal sign to get one equation, and then do the same thing for a second equation, I get two randomly generated linear equations, a set of simultaneous linear equations. Okay? If I do that, that would correspond to two random lines in the xy plane. So lines could be anywhere, angled any way. They could even conceivably be parallel, unless you're randomly generating the numbers from an infinite set. Okay, so if you randomly generate the numbers from a finite set of numbers, then there is a non-zero probability that you'll end up with two parallel lines. Now, if you have an infinite set of numbers, then there's actually zero probability that the slopes are going to match up. And also zero probability that the y-intercepts will match up. There are just too many possible points. And you can puzzle over that if you want. It's kind of interesting. Okay. In any case, there'd be a high probability if you use a large finite set, there'd be a high probability that the lines would not be parallel. From an infinite set, it'd be certain that they would not be parallel. Okay. I could write that in, but I don't think I'm going to right now. Okay, so if the lines are parallel, then the probability that they also have the same y-intercept, let's say, or the same x-intercept, would be very low. So it would be very unlikely that the two equations would be the same, would give you the same line. However, it's possible from a finite set. Much more likely that if you're going to get parallel lines, they would be apart from each other. So that's if you're randomly generating just plain old numbers. Now, if you're in the real world, there are situations where we maybe model some phenomenon where you might get parallel lines. Okay? It's much more likely when you're dealing with real world situations than when you're dealing with arbitrary sets of numbers. So we need to deal with these possibilities. There are also theoretical reasons. And I won't go into the linear algebra, which I teach right after this course, but that's where it is. Okay, so in any case then, if the lines are parallel, but I'm saying it down here, if they're parallel, they probably won't have the same axis intercepts, so there probably won't be any point where they intersect. Okay, I mean, if they are parallel and don't have the same intercepts, they don't intersect. For random choice, it's going to be very probable if you get parallel lines that they wouldn't intersect. It's still possible that they could have the same intercepts if you're dealing from a finite set. And I really need to mention this finite set, so. So everything from here down, if from a large finite set of numbers, we can make these statements. Okay. In any case, it is possible that the lines would consist of identical points. So every point on the line, on either line, is a solution. So every point we should say every point on the common line is the solution. So there's an infinite set of solutions. So what we see is, if the lines are not parallel, as in previous examples, you get a unique solution. The lines cross at exactly one point. Each line consists of all the points that satisfy one of the equations. So the one point that satisfies both equations is where they meet. If they're parallel and don't intersect, then you get no solutions. If they're parallel and do intersect, you have an infinite number of solutions. Every point on the line is a solution. There are infinitely many points on the line. Okay, so should have looked at this. It's been a couple of days since I did this. An example of lines that are identical. So here I've represented two lines that are identical, one in yellow and one in white. And I've kind of drawn them with a yellow segment, then a white segment, yellow segment, white segment. It's a little hard to distinguish yellow from white. So I'm going to go purple here, okay? So if you have these two equations, let's see what happens. Okay, if I just choose to match the coefficients of x, I'll multiply this equation by -3 to give myself a -6x here, which when added to the 6x then eliminates x. But look what happens. I continue multiplying by the -3. I get -9y and -18. And all of a sudden, this equation is the negative of this equation. So when I add the -9y and the 9y, I get 0. The -18 and 18 give me 0. In eliminating x, I eliminated everything else. And if I'd chosen to eliminate y, well, I would have done the same thing. I would have multiplied the first equation by -3, and this is still what I would have gotten. So the result then is 0 equals 0, which is always true. So any solution to either equation is a solution to both. And of course, if you want to do this geometrically, both equations have the same x and y intercepts. If you let x equal 0 here, y is 2. If you let x equal 0 here, y is going to be 2. So 0, 2 is going to be an intercept. And if you let x equal y equals 0, then x is going to be 3 here. If you let y equal 0, x is going to be 3 here. So you got 3, 0. 0, 2, 3, 0, same line. Okay. Yeah, right there it is, actually. And let me do my thing with the yellow and purple. So this is now my purple equation. And I've got my yellow equation. So the purple and yellow lines lie right on top of each other. If I have numbers here such that this number is not 3 times this number, in other words, if the left-hand sides are the same and this number isn't 3 times this number, then that changes the intercepts of one of the equations. And they won't be the same. The equations will be parallel, but they won't intersect. For example, if I change the 6 to a 12, okay, I get 2x plus 3y equals 12, 6x plus 9y equals 18. I do the same operations, multiply the first equation by -3, but of course I don't get a -18 to match the 18. I get a -36 in an 18, which gives me what? The left-hand side, as before, gives me, adding the left-hand sides gives me 0. Adding the right-hand sides gives me -18. I get 0 equals -18. Well, there's no value, there's no set of x and y values that will make 0 equal to negative 18. There's nothing that will make 0 equal to negative 18 except to put that in as a postulate in some mathematical system, for example, a mod 18 system. And you don't need to know about that. Interesting, not difficult. But not something we do in this course, okay? So, this is never true. There's never a set of x and y values that makes this so. So no solution. And of course, if we graph these two equations, we find the intercepts 2 and 3 as before, but the intercepts here are going to be 4 and 6. So now we have two lines of equal slope, and you can calculate the slopes and see that they're equal. Slopes are both negative 2/3, but they have different intercepts, so they're parallel, but they don't coincide, so there are no points in common. Okay, these geometric interpretations are very important if you go a little further in mathematics, especially if you take a linear algebra course at some point.